So we'll start our class, and this is flight mechanics class. This is day 1. We have successfully completed our aircraft propulsion and our aircraft structure. Now in core subject, you can consider this as our third core subject. Flight mechanics is very interesting topic, but it is not that hard as aircraft propulsion or aircraft structure. So students who are still practicing or about to complete the lectures of aircraft propulsion or structure, this is the good time for them, because from now onwards they can balance their pending lectures or syllabus, assignments, test series with flight mechanics. Same thing will go for aerodynamics as well. In case of aerodynamics also, you have to add some extra subjects with running lectures of aerodynamics. Okay. So with flight mechanics, you can manage any one large subject. You can manage propulsion or you can manage structure. If time permits, like you can also go for test series of both propulsion and structure at a time. Like it depends if you have not completed yet. So only like I have checked website, only 7 students have completed propulsion, structure, all the bits, test series, everything. Many students, they did not even complete half test series in these two. So I can say that roughly my complete class, all the students have to complete propulsion and structure test series yet. So slowly you guys complete assignments also and test series also as per your convenient, but don't delay now. With flight mechanics you can easily cover. Okay, it is not a tough subject, but see, when I say it is not a tough subject, still students are doing mistake in flight mechanics numericals. Subject is not tough, it is fact based subject. In flight mechanics, I will categorize in this way. In our flight mechanics course, we have, like if you see the GATE syllabus, that is divided, like I can say some basics you should know, that basics I will teach. After that, you are given with a topic called atmosphere. In atmosphere, you have subtopics. You can just see the PDF of the syllabus. If any new student is there and interested in this PDF, they can just ask me, I will give them and they can read the PDF. But it's okay, it is just about the subject classification. So no need to worry about that, because already I will take here everything in detail. Then we have something called performance. In short, we say performance. And actually, officially we say this aeroplane performance. So you can say airplane performance or aeroplane performance. One more thing I want to mention here, there are 2 words. One is aeroplane and one is airplane. So one is British and one is American English. You just cross check on Google if you're interested. Currently I think this one is British English and this one is from like American English. Same thing for airfoil also, like some people say airfoil, some people say aerofoil. So only this mistake, I mean not mistake, only this change. One is British and one is American. So then we go for, so airplane performance is very interesting topic. And after that, when we enter to stability portion, that is our 4th portion. Here I should take like this. We say stability. So in stability further we have 3 important classifications. So we have static stability, we have dynamic stability, and then we have some special cases. Okay, so this you can say like combination. After knowing static stability and dynamic stability in detail, then we discuss this. So I will explain one by one, slowly we will cover in this. And after that, we have some special topics. Dynamic stability comes under special topics, but again I have some special topics. In that special topics, you may have heard there is something called Euler angle, equations of motion, like when I will be teaching you dynamic stability, that time I will introduce equations of motion, okay, and some special modes I have. So these things I will cover. What kind of basics I am expecting you to know? Very basic, very basic basics, what we have already covered in our aircraft structure lectures, like idea of velocity, idea of force, moment, these things, basic ideas. In your flight mechanics course, what we are going to discuss mainly, that introduction I will give now. So, and consider one thing. Suppose this is our aircraft. Now in this aircraft, basically what we have to do in this chapter, we need to find out, I mean in this complete subject that I will filter here, basically we have to find out performance properties. What is performance properties? Like what are the basic maneuverings any aircraft is doing. Those basic maneuverings are no need to note down anything, just understand the history, then after that prepare some background, after that I will give you notes. See, we have to know that what is the complete nature of the aircraft during flight. We know that, suppose this is the runway, what happens if you have gone to any airport or you have taken any flight, you may be knowing that there will be one building, okay. I will draw the top view of the airport. Different airports are having different management system. So I am creating something here. Suppose this is the airport building, okay, and this is the civil road, like car, bike, everything goes here. So from here we enter to the airport. After entering the airport, we do our formalities. Then what happens? There may be situation that exactly from the airport itself, there will be aero bridge, or you can say air bridge, and your aircraft will be standing very close to this aero bridge or air bridge, and passengers will directly go to aircraft. Now, this is one situation. Another situation is aircraft is not standing here. Aircraft will be standing somewhere, okay, close to runway. So what will happen? Then there will be any service bus. On airport, we have some buses, okay, normal buses. They will be like AC buses. So passengers will take the bus, buses from here, and this bus will take to the aircraft, and then from here, aircraft will go to runway, and from runway, aircraft will go forward, okay. And if you are directly going to the aircraft, then aircraft will from here aircraft will go to the runway, okay. So every phase is having its own name, technical name. So you don't have to confuse in one thing what is your syllabus and what is happening in real life, okay. How people are talking outside about the aircraft, but how much we have to cover in GATE syllabus, that is really very different. Okay, I'm changing the page. So why are we making aircraft? To reach from point A to point B, right? So to cover point A to point B, how many things basically we do? We have runway. On runway, aircraft will be running, okay. After that, climbing. After that, cruise. After that, from here, aircraft will start descending, okay, like this. And after that, again, it will come down to the runway, right? So in all these things, how many parameters we are going to discuss here? See, first of all, we will discuss what are the inputs pilot gives to fly aircraft. All the members, whatever structural members we have in the aircraft, what is the role of every member? We are going to discuss that. We will also discuss all types of phases in detail. Okay, what is takeoff, what is landing, what is climbing, types of cruise, spatial maneuverings, and we will discuss that we call as performance. And we will also discuss, there is very important factor we call that as stability of the aircraft. In that we have two types. Now see, but in today's class, we will not discuss all these things. In today's class, we will discuss our first basic unit, atmosphere. Why to discuss atmosphere? Because one very important lesson is, suppose in future you are going to start a company. Okay. Now in this company, suppose this is any Indian company, and you are going to produce manufacturing all types of aircrafts. Now you want these aircrafts to fly in India. So I will consider one thing. Whatever aircraft I am manufacturing, that will fly in Indian atmosphere. Indian atmosphere means in our atmosphere. Okay. But suppose if any foreign country who is not having facility of manufacturing the aircraft, or they are not involved in aircraft manufacturing, but they want to fly their passengers, so they will purchase your aircraft. In that case, this aircraft should be capable of flying in their atmosphere, right? So this is one thing which gives you strong logic to understand about atmosphere, basics of atmosphere, and of course GATE syllabus. Okay. Now suppose in India itself, if I draw the rough map, I'm sorry, I'm not good at that. Something this kind of, I'm very sorry, don't offend. Something. So you will fly. Suppose in this region atmosphere is different, but in this region atmosphere is different. So in India itself we have different atmosphere. Okay, one more thing you should know. Mostly if you check either Airbus or Boeing, these two companies, they are manufacturing the aircrafts. Either Airbus or Boeing. Actually it is kind of, if I'll club both the companies together, then you can say kind of monopoly. Okay. But of course we have lot of other aircraft companies, they manufacture this. Don't be confused. Manufacturers are different. Okay. But airlines are different. What is difference? See, manufacturer, they are going to manufacture the aircraft according to the need, and airline companies are those companies who will take these aircrafts and fly. Okay. So these companies, airline companies, they will hire pilots, crew members, and other technicians. Okay. I can ask one genuine question. If you are aeronautical or aerospace engineer, then for which company you are doing your study? So direct answer, you are not studying for airline companies. Definitely jobs are there, you can apply and you can get the job, but aeronautical aerospace engineers are actually doing study to join manufacturing companies, okay, where they can do all design thing and R&D things. Mostly we are, means aero people, we are interested in R&D, like what we think like, okay, what kind of new design we can introduce, what kind of new logic or concept we can introduce in the system, so that in coming future aircraft can be light and aircraft can have better efficiency and we can save more fuel, so that cost of flying will go down. Okay, lot of other things are there. Slowly this subject will be very interesting. Let's start our chapter atmosphere. So just heading atmosphere. Okay, and you can do one more thing. Some students still, they may not be parallel with me, like you may have half completed aircraft propulsion or partially, same goes for aircraft structure, but I think almost new students and all the students, they are restarting now, so at least flight mechanics you should be parallel. Okay, and slowly those subjects you cover, because if you will not cover flight mechanics and if you will be bothering structure and propulsion, then again you will not be parallel to me. So be parallel from now onwards. So what should be your daily schedule? After my class, some students are taking class notes here itself. Very good. So first thing is notes. Then next thing, some assignments. Then next thing, some important PDFs I will give you to read those PDFs. And these things you have to go through some important topic wise test series. So this much you will do, topic wise and subject wise test series, this much you will do. Okay, so this much I am expecting from you, and definitely I'll be available to take your doubts, because immediately after this I will start aerodynamics, and then you will see that almost syllabus over. Then we are remaining with rocket and space. They are not very big subject, and parallelly we have already started engineering mathematics. Okay, so take down your heading for atmosphere, and now take down your first topic. Okay, very good. So let's start. So this will be kind of this chapter will be kind of theoretical chapter. So first of all, you take down need to study the atmosphere. What is the need to study the atmosphere? Okay, so actually you write down here, flying vehicles are classified into two main categories. Okay, two main categories. First category is your atmospheric vehicles. Atmospheric vehicles. Just example is enough. Those vehicles, they are going to fly only in the atmosphere, within the atmosphere. Atmosphere means sensible atmosphere, where sufficient oxygen is there for the propulsion. Okay, so vehicles can fly only in sensible atmosphere. Example you can take down like airplane. Okay, and drones are also there, right? Nowadays drones are very popular. Drones, helicopters, and you should also write down bullet. Okay, bullets, and you can also write down some special missiles. Not all, some missiles. So I hope you understand why I am taking example of missile also, why I am taking example of bullet also. See, if students are having interest in defense side means if you want to do job, or if you want to study about bullets or missiles, especially types of bombs, okay, guns. So there is a institute in India. They work especially for these kind of studies. So you can also do your master degree in these kind of studies. But I am not sure about placements things. So that we can, if any student will apply for that college, that time we can, because some students they have been there, so I can ask them what is the current situation of that college. Okay, so but anyway, mostly most of you are targeting for IISc, IITs. So mostly what happens when we don't get IISc, IITs, so we try for that college, and some students they join that college out of interest because of the subject of defense thing. Yeah, jetpack also is a very latest example. There is industry, there is a company called Gravity. Those people are making very good jetpacks. You may be aware of this Akshay Kumar, actor, Indian actor Akshay Kumar. He tried that jetpack suit. Okay, you can check that on YouTube, Gravity Industry, their videos. They use a jet engine in their suit, and they control jet engine very nicely. So okay, fine. So one is atmospheric vehicle, and what is another one? Another one is very clear, space vehicle. Space vehicle. Space vehicles. So space vehicles are having atmospheric vehicle features also, plus additional feature, they can also go out of the atmosphere. In that deep space they can go, right? So example, just you write down very popular rocket, then you can take other space shuttles. These two are enough to understand what kind of thing I am saying. So you know what, actually in aeronautical engineering we don't study rocket and space, but in aerospace engineering we study rocket and space as a syllabus. But in some aeronautical colleges they offer us space science as elective. Okay, so it depends on university. Because in India, all the universities are not having exactly same curriculum. Little bit difference is there, but it's okay. That's why for GATE exam they classify proper syllabus for this. Okay. I'm changing the page. So as I said, on our globe we have different countries. Almost in every country aircraft is being used, and different countries are having different manufacturing setup for the aircraft. We have some critical situations also, like we have pole, right, where atmospheric condition is really very difficult, and we have space studies also. There we are launching our shuttles. So point is, everywhere we have different atmosphere. Okay, so all the related people of this field, all the scientists and engineers, they came to a suggestion, and they decided to define ISA, International Standard Atmosphere. This is nothing but a mathematical set of values of temperature, pressure, density, etc. Okay, so that we considered as International Standard Atmosphere. So how do they get this idea that okay, there must be this value for pressure, this value for density? So what they did, from different countries, they measured their atmospheric values and they took average by using some analysis, some model or something mathematical way, and they came up with the proper idea. And they said this particular set of temperature, pressure, volume and blah blah things we say as International Standard Atmosphere. So idea is, above the India we have different values of our atmosphere. Above America we have different values of our atmosphere at different locations, but still we take a different value for the International Standard Atmosphere. And in GATE exam, I think just before 1 or 2 years, they asked one property, direct property, what is the value of temperature, pressure and density, like that they asked. So you take down your new heading as International, you write down full form, Standard Atmosphere. So in that you write down properties like temperature, pressure, density. Not only this, viscosity, etc. change with time, altitude and location. Okay, you understand what is the point. Suppose I am standing right now, I am sitting in my campus, you are sitting at your home. So we all are in India now, so we have different in locations. So locations are different. Morning you face different temperature, I face different temperature. Like if you check on Google, my location Dharwad, this will be having different altitude, your location will be having different altitude. So these are the factors. Because of these important factors, sunlight, actually what happens, main feature why we have different atmosphere, sunlight. Because of sunlight, different part of earth will be getting different intensity of light. Because of that, local air density will change. Because of that, these air molecules will start shifting from high density to low density. So when this is happening, when density is changing, then what we see physically air. Okay, if there is air, if you feel air, it means density, air is flowing from high density to low density. So whenever you see this next time, you try to feel in this way. If you feel air on road, on your terrace, so you check the direction, then you can easily judge where density is more, where density is less. Not only this, you can also enjoy by imagining one situation that suppose you are standing here and air is coming from this side to this side. It means here density is high, here density is low. Then you can also judge some more phenomena, like which side temperature pressure will be high, which side temperature pressure will be low. Okay, you will not get the exact idea, but you can feel. Anyway, nowadays internet is there, you can just type humidity, density, temperature, pressure at this location, so that is also a very good tool. But you can feel this, you can also feel in your way. Okay, fine. ISA, it doesn't work. It gives us a standard value. Like in our calculation, mathematical calculation, everywhere we put same value. All the engineers around the globe, they use the same set of values. Okay, it is not like physically there is nothing called international atmosphere. Okay, for example, you may have heard, no need to be confused, you may have heard that we have one English channel, right? People swim and they cross English channel and they make some records, right? You may have heard this about this English channel, something like this English channel. You may have heard, right? So it's not like something English. Yeah, name is English channel. So international atmosphere means it is set of values. So you take down that also. Definition. Yes. Because see, that is an average data. One more point, that is an average data. One more point, if you are making aircraft in your own country, then in your own country also temperature, pressure and those things are not constant, right? If you go altitude wise, that is not constant. So actually we came to know that around the globe, what can be the maximum extreme condition in which aircraft should fly, right? So how will you come to know that about that extreme condition without deciding any factor, right? So some experiments happened. Take down definition. The imaginary set of values that are assigned to the physical properties of atmosphere at various altitudes by an international agreement is known as International Standard Atmosphere. Copy down this. So actually whatever values we are talking here for temperature, pressure, blah blah things, they are not a constant value. Even they change with time. They change with altitude. So we have set of values which are constant at mean sea level, but even these values are the function of altitude. Okay, so for that I'm changing the page. Take down this is 0.1, then go for 0.2. 0.2 you take down temperature, pressure and density etc are the function of altitudes and given by ISA. Now take down third point. These values are you take down like this: by using experimental balloons, sounding rockets, and sounding rockets, we get the mathematical model of atmosphere. Okay, now you take down ISA is used as standard to relate or compare the wind tunnel test, general performance of aeroplane, special flight tests, etc. Copy down this. So now you take down properties of ISA. Properties of ISA. So see here, whatever we will write here, that we will write at mean sea level. Okay, so here we will write at mean sea level. So here first property, the symbol is T naught, 288 Kelvin. Second, P naught, 101,325. Now here Newton per meter square. Then third one, rho naught, 1.2256 kg per meter cube. Then mu naught, 1.784 into 10 to power minus 5 unit kg per meter second. Then nu naught, see here, dynamic viscosity and kinematic viscosity, these two are different things. Okay, on this dynamic viscosity and this kinematic viscosity, how to feel what is the difference in both, I have made a video on YouTube. You just write down like dynamic viscosity, kinematic viscosity, concept library. So this video will come and you can see the differences and you can feel exactly what is the main difference between these two and how to feel this. So this value you always calculate, kinematic viscosity we always calculate using formula mu naught by rho naught. It means actually naught I am representing here because here I have using naught, but mu by rho is actually the main formula. So mu by rho, this will come 1.4556 into 10 to power minus 5 meter square per second. Now I will tell you one thing. If these properties you will mug up, then this would be very easy for us to use directly in the question. Otherwise, remaining, like mostly students, they remember T naught value, but in P naught value, when it comes in bar, when it comes in Pascal, megapascal, they used to be confused. So make your basic strong. Values you should never never feel like it is hard or not able to recall. So you do one thing, very important thing. You write down these values, take photo, make wallpaper, and from your home screen you remove all the apps for few days and make this value as your wallpaper. So many times when you will see this 2-3 times in a day, then all the values will come in your mind. This would be a very good thing. Very long back this is meter square per second. Meter square per second. In my time when I was preparing for IIT JEE exam, that time audio recorder was there. This I purchased this thing. I forgot that we say AirPod something. Some AirPod something was there. I purchased that was from Chinese company. So I purchased for study purpose. Like I was having weak concepts that time in my 11th 12th when I was preparing for this thing. So whatever I used to understand, next day I used to forget the main concept. So I used to record them and I used to save and I used to listen again. Like what was the trick, what was the concept here, step 1, step 2, step 3, like that. So nowadays things are there, you can also do like this. Okay, so now these are the properties, but these properties are the function of altitude. Okay, so when altitude will change, these properties will change. So we will understand how properties are changing, and because of the behavior in these properties, we decided different layers in the atmosphere. Okay, different layers in the atmosphere. I will take this chat. Is it like a specific location has different? No. For entire globe, we have only one ISA. When you will study aero studies in other countries, anywhere, Germany, Japan, America, anywhere, you are going to solve same set of problems. Unit wise, it can be different. Like we follow SI unit, some other country may not follow SI unit, but same set of properties we are going to discuss. Okay, if for Indian students, if temperature is 288 Kelvin, then at mean sea level, everywhere this will be the same 288 Kelvin. Okay, only thing is some other country may not be using Kelvin, so there is a formula to convert 288 Kelvin into some other units. Okay, but they will be same. Okay, so I was saying, because these properties changes with altitude, so because of the behavior, we took one property to decide layers in the atmosphere, and majorly that atmospheric layers are based on temperature. So you will see these kind of graphs if you will check any standard book. You take any standard book, or you can just Google also layers, atmospheric layers, something. So you will see, suppose this is your altitude, and for example this is your temperature. So currently, of course, we don't have 0 Kelvin temperature, right? At our Earth surface, we don't have 0 Kelvin temperature. How much we have? So according to ISA, we have 288 Kelvin temperature. Okay, so students may be thinking that if this is our Earth and here we have sun, so when you will go towards sun, then temperature will increase always. But this is not true. What happens? P is equal to rho RT is an equation, right? We know this equation, gas equation, ideal gas equation, anything you can say. So this you will change. P by rho R is equal to temperature. Now check here. See, actually, this R, if I ask what is R value, if you have done my thermodynamics or gas dynamics course, then you know that this R changes according to the gas. So you know that in our atmosphere also, oxygen is not present everywhere. In our atmosphere, gases are differently present, mixture is present, ions are present. So it means what? Gas is changing. It means R value is changing. According to that, you see, density is also changing, pressure is also changing. So according to that, your temperature will be decided. Okay, temperature is decided because of these factors. So what happens? Actually, when you go up, only one situation you understand. I'm changing the page, I'll come back to this page. This is your Earth. Suppose this is your sun. So when you go up, what happens? Pressure will also decrease, density will also decrease. Correct? Okay, understood this much. Pressure will also decrease wherever you go, till we consider roughly 500 kilometer as gases are present. After that, we consider, okay, now you can say roughly we are entering into deep space. Okay, now in other textbooks and other professors, other lecturers, they explain this height differently. You can judge any textbook, you will see that they say that till 11 kilometers you have troposphere, but some other textbooks will claim 15, some may claim 14. No, but no problem, it's okay. So what I will be giving you, that will be there for your GATE exam, which value I will give you. Okay, so my point is, if pressure is also decreasing here and density is also decreasing here when I am going up, then you check the equation. P by rho into R is equal to T. For time being, just to make situation more simple, I am not discussing about R variation. Let's discuss only P and rho variation. So it means temperature is depending on P by rho. Temperature is not depending on P alone. Temperature is not depending on rho alone. So what happens? If in any atmosphere temperature is decreasing, okay, and you know already P is also decreasing, rho is also decreasing. These two people are set always. Pressure and density variation, this is always there. Pressure will also decrease, density will also decrease when you will go towards sun. I mean when you will go away from the earth's surface. What will happen? If I am saying that in certain atmospheric layer, your temperature is constant. What does it mean? Whatever decrement is in pressure, same decrement is in density, and that is compensated so that your temperature is exactly constant. If I say pressure is decreasing more faster than density, then what will happen? Listen my word. Pressure is decreasing more faster than density. It means density is also decreasing but slowly. Then what do you say? Temperature will decrease or temperature will increase? Tick on my screen, students. All the students, what do you think? Everyone is okay, fine. You guys are correct. So if pressure is decreasing more faster than density decrement, then temperature will decrease. And if they both are decreasing in such a way that the final variation is constant, so it will be constant. So actually, based on these kind of behaviors, we decided our layers in the atmosphere. Okay, so now I am coming to the layer. So we are going to bother mainly about those layers where atmospheric vehicles will fly. Okay, so I will bother about 11 kilometer and I will bother about 25 kilometer. Okay, other than that also we have variations. Okay, but I will not bother about that because we are not going to study geography or atmospheric science in detail. We are going to understand only little bit. Okay, so when you will go up, then there will be certain temperature because temperature will decrease, and then temperature is constant. So this is the temperature variation curve, right? So here this layer of atmosphere from 0 kilometer to 11 kilometer, we say troposphere, TROPO, troposphere. And then from 11 to 25 we say stratosphere, strato, STRATO, stratosphere. Okay, and again this height may change. If you Google, then different websites may claim different altitudes. Okay, so this line, or you can say this layer, which will differentiate troposphere and atmosphere, that we say tropopause. This line we say tropopause. Then again we have layer, then this line you will say stratopause, then again we have layer like that, but we don't go into that detail because of our syllabus limitation. Okay, so you can see here in this atmosphere, I mean in that layer, you can say in troposphere, your temperature is decreasing. So how fast your temperature is decreasing? Okay, how fast? Like on every 1 kilometer, how much temperature drop we see? Okay, so understand that point. Here for this diagram, you say heading as layers in atmosphere. This will be your heading. Under that, you draw this and then you write down these important points. I'm changing the page. You write down what is lapse rate. Okay, so it is lapse rate we show by lambda here. It is the rate of change of temperature with respect to altitude. So here how do you solve this? So lambda is nothing but dt by dh, rate of change of temperature with altitude. Now see, this can be positive, this can be 0, this can be negative also. Okay, means if temperature is constant, then no lapse rate, 0 lapse rate. If temperature is decreasing with altitude, then negative lapse rate. If temperature is increasing with altitude, then positive lapse rate. Okay, so when you will further open this guy, then it will look like T2 minus T1 by H2 minus H1. Okay, now if I consider H1 is equal to 0, it means mean sea level. And if I consider H2 as any altitude H, okay, this altitude at any altitude in troposphere, and for this mean sea level, this T1 I will consider as T0. Okay, and this at this altitude, whatever is temperature, that is T2, that I will consider as normal T, or you can say T at altitude H, TH. Then I will gain this formula. So this I will write as TH minus T0 is equal to H minus 0. So you club this equation, split this with lambda, then you will be getting equation as TH is equal to T0 plus lambda H. Okay, this became your equation of temperature variation with altitude. Okay, in troposphere. Okay, so when to use this equation? How are you going to? So currently we are going to use this equation. You can use this equation in any type of layer, but because our study is limited, so you know that for our study purpose, this equation we are going to use from where to where? From mean sea level to tropopause. This equation you will use, right? Okay, so we can solve. So we should know what is lambda value. Lambda is constant for every layer. So for troposphere, you just take down for troposphere your lambda value. See here, I will write two values, minus 6.5 Kelvin per kilometer, and I will write minus 0.0065 Kelvin per meter. See the difference. This data is for per meter variation. This data is for every kilometer variation. So don't be confused. Okay, so troposphere, you can calculate temperature by this. We will solve one small problem. What will be the, this is your example, what will be the ratio of temperatures at 8 kilometer altitude to the temperature at 5 kilometer altitude from mean sea level. Okay, answer in 2 decimal places. Okay, so give me answer in 2 decimal places. Okay, first and fastest answer will be appreciated. Do it fast. If students are confused, you have to find out T8 by T5. Do it fast. Okay, back to back 2 answers I got. Other students waiting for a reply. Okay, I got third answer, fourth answer, 0.92. Very good. Good going. You guys are doing good. Very good. Okay, so for other students who are confused how to solve this numerical, I will explain this now. It is very easy numerical. I'm changing the page, or here itself I can explain. See, we need to find out temperature at 8 kilometer. So T8 is nothing but T naught plus lambda into H. Okay, so I can write T8 is equal to this T naught value I know 288. Lambda value you have to put minus 6.5. Now focus here. Everyone please unmute. You see, focus here. Please mute some students. Okay, minus 6.5 you have to put here. You can't leave this minus sign. Okay, you can't leave this minus sign. You have to put that minus sign. If you will miss this minus sign, then it will be a positive lapse rate. Then your numerical will be wrong. In troposphere we have negative lapse rate. Okay, and just multiply 8 here. So what I was saying, kilometer data you are using, so kilometer will get cancelled, so Kelvin will be remaining. Okay, by mistake if meter is given, then you should use this data. Okay, that is your own focus, which mistake you are doing. So T8 value calculate like this. Exactly T5 you calculate as T naught again means 288 again plus minus 6.5 and then 5 and then take ratio. So T8 by T5 you have to take. Very easy. 0.92 will be your answer. Okay, so I will take further numericals about this. I'm changing the page. Type down question. What will be the ratio of, okay, no, what, directly take this one. What will be the temperature at 13 kilometer? Do it fast. Let's see this time who is giving first and fastest answer. For this question you are saying your temperature will be 0.92. Now see, actually I am asking what will be temperature at 13 kilometer altitude. So some students are asking above at troposphere something. No. This is IQ based problem, guys. IQ based problem. Many students, I know you guys are seriously doing something in your mind. This is IQ based problem. Many students are doing mistake here. Many students. You forgot in hurry that troposphere is only till 11 kilometer. Okay, so you can't use this equation TH is equal to T naught plus lambda H. You know why? Because your troposphere is only till 11 kilometers. So this is limited only till tropopause. But I have given you 13 kilometer. It means this question went to stratosphere. And you know, in stratosphere, temperature is constant. So whatever is temperature at 11 kilometer, same temperature will be maintained till 25 kilometer in till stratopause. Okay. So It means you need to put this H value as 11 kilometer, and from 11 kilometer to 25 kilometer in stratosphere temperature will be constant, right? So I can also ask you in 14 kilometer, in 15 kilometer, so that is going to be the same answer. So at 11 kilometer when you will calculate, it will come 216.5, 216.5. Other students, please verify whether you are getting the same answer or not. 216.5. Very good. Other students are getting 216.5. Very good. Fine. So very good. Now by using, very good, everyone is getting to 16.5. So you save this in your mind. See here at 11 kilometer, here, exactly here, you write down this data you write down here, temperature is 216.5, and you just highlight, this will be in your mind always, okay, that from tropopause to stratopause, that will be your temperature. Okay, so we have learned how to calculate temperature in different layers. Now we are going to learn how to find out pressure and density at different altitudes. So I am changing the page. Take down pressure calculation in troposphere. So currently we are learning for troposphere. So you have formula. At the same time you write okay, because we have taken heading, no problem. So you will use P2 by P1 is equal to T2 by T1 minus G by lambda R. This is your formula. No, this formula is applicable for any zone, this temperature formula, but only lambda value will be changing. So because I have given you lambda value, so see here, like what she is asking, this T naught, sorry, TH is equal to T naught plus lambda H is valid for any type of layer, but your lambda value will change for different layers. How much we are focusing? Only two values we are focusing. We are focusing, one is minus 6.5. Yeah, this lambda is only for troposphere. In different spheres, lambda value will change. Okay, fine. Because the remaining atmospheres are not of our interest, that's why I'm skipping this. Let's go ahead. So minus G by lambda R. See here, this lambda value in this formula, you will substitute the same lambda value what I have given. So because we are learning for troposphere, so just mention here lambda will be minus 6.5, same lambda value, Kelvin per kilometer, or minus 0.0065 Kelvin per meter. Don't be confused. Okay, and what will be your R value? So R value, you will take that normal R value what we take for air, because we are not going into detail of the combination or mixture of gases. No, we are not making that complicated. So whatever R value you have used in gas dynamics for air, same R value you will put here. Don't worry, I will explain about that R value also. So by using this formula, so okay, point is, how are you going to prove this formula? So we have some set of ideas, we club them, like we use, to prove this equation, we use TH is equal to T naught plus lambda H. Okay, this formula we use. We also use P is equal to rho GH formula. So this is hydrostatic law, right? This one, hydrostatic equation. So by using this, and we also use P is equal to rho RT. So by using these three equations, we prove this equation. Proving is not important. That's why I am not writing proving here. Okay. So in same way, we also go for your density calculation. So when you calculate for density, you will write down, just write down here density calculation in troposphere. So exactly similar formula you will see, but with minus sign. Rho 2 by rho 1 is equal to bracket T2 by T1, now bracket close. Now here you will write down same whatever power is there, minus G by lambda R, but in this power you subtract minus 1. See here, don't be confused. This -1 I am subtracting from this throughout minus g by lambda r. I am not subtracting this -1 from lambda r. Don't be confused. It means I can put one bracket here and one bracket here. Okay, that -1 is subtracted from all the three things. Totally clear? So we got set of equations. So we can solve one question also for the pressure and density variation. That is very easy. So let's check you guys are able to crack that question or not. I am changing the page. Have you taken down? Good one. I am changing the page. So everyone please give the correct answer. Be focused. Calculate pressure at take down 10 kilometer pressure 10 kilometer from mean sea level. So how will you calculate pressure? Okay, first it is your thing. You give me answer. Let me check you are getting correct answer or not. Give me answer in 1 decimal. Give me answer in 1 decimal. 1 decimal. Okay, and give me answer in Pascal. Pascal means Newton per meter square. Some students are not able to find the correct answer. And Priyanshu, your pressure is increasing. Pressure should decrease. And some students, okay. So this 26396.5 is absolutely accurate answer. Sanjana, your answer is correct. 26396.5. This answer is correct. 0.5 answer is correct. But how will you find out that? So let's see the solution process. Easy, very easy. P10 by P0 you can use. See, main formula is here. Where? Here. So in this formula, this P2 and P1 you replace with P10 and P0. We can do that, right? So here you replace with 10, here also 10, here not, here not. So P10 by P0 is equal to, T10 value is nothing but T0 plus lambda h divided by T0. Okay, minus G by, okay, this minus sign also you can remove because lambda is already negative. So G value I am using as 9.81 divided by 6.5 into R value 287 you have to use. Okay, so for better calculation you can divide this guy. So P10 by P0 is equal to 1 plus lambda value, this will make you negative. So 6.5 into 8 value, if we are using kilometer data, so 10 kilometer, divide by T0 value 288. So like this if you solve, your solution will be somewhat more closer to the decimal point. So this P0 value you have to put 101325, then this P10 will come as why we are using kilometer, right? Oh yeah, you are right, because data, yes, you are absolutely right, because G value is in meter per second. Thank you. G value is in meter per second. See, I was about to attempt a mistake. Actually here G value we are using in meter per second. Kilometer is not SI unit. Be very careful. So in this question, because G value is also involved and other data like 287 is also involved, they are SI units. So kilometer is not SI unit, meter is SI unit. So I was about to do mistake. So thankfully we now I am safe side. So your correct equation will be P10 by P0. You will use as, I am writing complete. 223 you will be getting temperature at 10 kilometer and 288 temperature at mean sea level. Then 9.81 divided by 0.0065 into, this will be 287. If you solve this, then you will be getting this value will come 0.20 like 2605 into this P0. So your P10 will come as 2639.6.5 Pascal. Copy down this. Okay, so we have calculated. So we got the idea that here exactly at mean sea level we have temperature, and that temperature is 288. When you will go up exactly at 11 kilometer, you have temperature 216.5, and but your pressure and density, they will continuously decreasing. But again, for this troposphere they will uh, decrease with different formula. For stratosphere, pressure and density will decrease with different formula. Okay, so, and you know that temperature is constant in in stratosphere. So now you are going to write down formula for your stratosphere for pressure and density variation, because temperature is constant, right? So you write down pressure and density variation in stratosphere. So actually what happens, both are decreasing but formula will change. So first thing, very important line you write down, temperature is constant at 216.5 Kelvin in stratosphere. Second point you write down, your your pressure at any altitude h. Okay, or you can write 2, P2 by P1 is equal to exponential E power minus bracket close G division R TS. TS, you understand that value which is constant means 216.5. Okay, this value you have to multiply with another bracket H2 minus H1. So we have limitation for this formula, and the same ratio goes for rho 2 by rho 1 also. Okay, see here. For this formula your limitation is 11 kilometer to 25 kilometer. Okay, means only for troposphere, sorry, stratosphere, only for stratosphere. Okay, now what is H2, what is H1? So whatever H1 H2 values you are taking, they both will be under the limit, means H1 and H2 both will be under limit 11 to 15, right? I hope you understood this part. Okay, we can calculate one small problem. In GATE exam, this topic is like optimally favorite. So it is not extremely favorite. Sometimes we have, but whenever question will come from this unit, that will be very easy problem. So self-study students, students from other coaching centers, everyone will be able to solve these kind of problems because they are directly formula based problems. So I am taking one question now. So I am changing the page. So now problem, why these questions of stratospheres are somewhat lengthier, because you should have data at 11 kilometer. This TS value already we remember 216.5, but in that case what is your H1 value as reference, what is your H2 value required, what is your P1 value depends on H1. Then only you can calculate your P2 value. G and R we are going to take same what we are taking, 9.81 and 287 always. Okay, so I am taking one problem here. So take down question, calculate temperature, pressure and density at an altitude of 13,000 meter in ISA. Okay, so this temperature pressure we already know. So solution, if you go, we know T naught value in advance, we know 88, and TS value also already I know that at 11 that is 216.5 Kelvin, and P naught value also we know 101325 Pascal or Newton per meter square. So then we can actually go for solution. So because they are also asking density, so density value you should be able to recall immediately. So rho naught value will be 1.2256, and guys, see, when you will go for your MTech MS degree, right, these values should be on your fingertips. Okay, because when I do experiment in my lab, so it is advantageous for me having basics very strong, values are on my fingertips. So my colleagues, they go to Google for something, for few things, but I used to recall immediately because of teaching part. So that is very, very easy. So remember as much as possible data, and main thing is Google is there, but impression also matters a lot when you are working with your colleague in same team. So okay, fine, we can calculate pressure at 11 kilometer. So because if you know pressure at 11 kilometer, then only you can calculate pressure at 13 kilometer, because both formulas are different. So your first job is calculate pressure at 11. Okay, then this 11 pressure you will put in 13 kilometer formula to calculate 13 pressure. So you will apply P11 by P naught, means troposphere formula first you apply. I will write down in detail. First use troposphere formula. What is that formula? P11 by P naught you can use, that will be equal to T11 by T naught minus G by lambda R. So see here, P naught value I know, T naught value I know, TS means T11 value I know. Okay, I know R value as 287, I know G value 9.81, substitute lambda value minus 6.5. When you substitute all the values, you are going to get your final answer. So in that final answer, you are going to calculate P11 as, I am writing direct answer, 0.36, sorry, 22,593.77 Newton per meter square. This is Pascal. Okay, 22,593.77. This is your P11. Now if you know P11, then only you can go to stratosphere relation, right? I will come to that. You also calculate rho 11 here, because rho also we have to calculate in the formula. So rho 11 by rho naught. How will you calculate rho value? T11 by T naught as it is. Now see, one more thing, there is a trick. That trick I will explain very soon. But first I am going for a conventional method, then I will explain the trick. T11 by T naught minus G by lambda R minus 1. This is the formula. Okay, but actually we already know that this much part is your pressure ratio, I mean P11 by P naught. So actually you can split this and you can solve, because already you have got value for this much. Anyway, currently because I am giving you solution, so you understand my trick also, right? So for rho naught value, data is there, T naught everything we know. So rho naught value I am writing here, I mean rho 11 value. Rho 11 directly copy down from my solution. Rho 11 0.3635 kg per meter cube. Okay, so we have done calculation for this thing. Now students, be careful. If you directly remember this data and this data, then in GATE exam Other students will calculate and then they will go to 13 kilometer. But you can directly use P11, rho 11 and T11 data for stratosphere. Why? If some students are weak in structure and propulsion or mathematics, they can they can save their time with these kind of tricks. Okay, be careful. Remember these data directly on your fingertips. Only till Feb month. After that, you can erase your memory. I am changing the page. Now go for stratosphere calculation. Use stratosphere formula. So you have only one formula for stratosphere. That formula is P13 by P11 is equal to e power minus g by RTS bracket H2 you will write as H13 minus H11. Okay, and the same formula you will use for rho 13 by rho 11 also. So see here, G, R, TS, every values you know, everything you know. H13 means 13,000 you write, 11 means 11,000 you write. When you subtract, then 2, okay, 2000. So P13 directly you copy down 1647.6.1. 1647.6.1 and rho 13 will come as 0.265 kg per meter cube. Okay, copy down this. Now I am taking very important topic. That topic I am taking as for dynamic viscosity. We used to calculate for troposphere also, stratosphere also, but that is free from atmosphere concept. Dynamic viscosity variation is not based on your attitude or these kind of formulas. It is given by Rayleigh formula. So I am changing the page. Take down dynamic viscosity calculation. So first thing, Rayleigh formula, Rayleigh, Rayleigh's formula. What is that formula? Mu2 by mu1 is equal to T2 by T1 whole power 3 by 4. Now see here, in this formula you don't have limitation of altitude. Okay, so in stratosphere, in troposphere, it is applicable anywhere. If I will give you temperature, one temperature of troposphere, one temperature of stratosphere, it's okay, we can use that. I hope you understand what I'm trying to say. You don't have limitation for the altitude, that why same formula for this as same formula. No, it is free from altitude formula. Okay, so take down, because already temperature and all we are calculating using altitude only now. So write down one very important note. Temperature is constant in stratosphere, so mu is also remains constant, but nu varies because it depends on density also, because nu depends on density also. What is nu? Nu is kinematic viscosity. For symbol you can write on, otherwise you will be confused. Your mu is dynamic viscosity. Today after class you watch that video on YouTube. Okay, dynamic viscosity, kinetic viscosity, physical field, concept library you type, it will come. Dynamic viscosity, and nu is your kinematic, not kinetic, kinematic, lengthy name, kinematic viscosity, mu and nu, right? Okay, so we got both. We'll solve one small numerical. I am changing the page. take down like this. Question. What will be kinematic viscosity at 13 kilometer? So see, because you need at 13 kilometer, so what should be your first approach? You will apply nu 13 as mu 13 divided by rho 13, correct? Just now we have calculated rho 13. Okay, that data I can substitute here, but you need to calculate mu 13. To calculate mu 13, you can apply Rayleigh concept, Rayleigh formula. What is Rayleigh formula? Mu 13 divided by mu naught is equal to T13 divided by T naught. Now whole power 3 by 4. See, this formula I am using directly without altitude variation. Okay. So 3 by 4. You can check here. One temperature at mean sea level, one temperature at stratosphere. Meanwhile, I had tropopause, but I hope you understand. So when you will apply this formula, all the calculation already we have. Mu 13 you will be getting as 1.44 into 10 to power minus 5, and answer will be in kg per meter second. Okay, this data you substitute back here because we have all the data just now we have calculated. Mu 13 done, rho 13 already we know, so your nu 13 will come as 5.44 into 10 to power minus 5 meter square per second. Just a moment, I have made a mistake. This is your mu value. This 5.44 is your new value actually. I should put here new, means this value. This value, new value I am getting as 5.44. This mu 13 is here. Mu 13 is here, 1.44. Thank you. Now let's understand a new topic in atmosphere, that is stability of atmosphere. Stability of atmosphere. See, many of us, we have done flight journey, and during flight journey you may have experienced turbulence. Okay, turbulence is not very serious thing. Because of turbulence we feel vibration in the aircraft, and during turbulence also our aircraft used to be stable. Okay, even if pilot is sleeping, we give enough design condition to our aircraft to be stable in the turbulence. Okay, you may have heard that nowadays we have completely like autopilot landing, like even landing can be completely automatic. Okay, fine, but here we have a topic, stability of atmosphere. What is that? Imagine this, my whiteboard, completely what you are seeing on the screen. This is your atmosphere, like completely everywhere you have atmosphere, everywhere you have atmosphere. Okay, so I am trying to judge, suppose there is a flight. This flight has to pass through this region, and flight track was decided like this. Okay, this was the flight path decided like this. Okay, one more thing, flight route design. In flight route design also you can do job. Okay, some of my seniors and my friends, they work in those companies also. They used to decide flights, like what is the path today for the flight. So actually, see, someone may ask that why aerospace engineers are going for these kind of jobs, because our jobs should be design and manufacturing, research and development for the aircraft, right? But why are we going these kind of things? Because see, aerospace aeronautical engineers are also going for bank jobs, railway jobs. So I don't have logic why. So economical issues, life settlement, lot of things, marriage, family responsibility. So wherever people are getting job, they are joining that, because in the last, finally, what matters? How much knowledge you have? Who cares? Even that book what we purchase from the shop, even that book is loaded with the knowledge. But when it is of no use, we sell this book to kabadi wala, right? Same thing will happen with you also after being aero engineer. If you will not earn, then the society will not accept you. So same thing. So that's why people go for different jobs. I consider two things. Job is definitely a problem for us aero people, but if you are sufficiently good, you can find your corner. That is also true. You can find your corner. Difficulty level is there in all branches. Even MBBS people, they are suffering for job after completing their this thing, medical thing. Okay, fine. So what is the meaning of stability? Okay, things are there. We are improving. In India also, things are there. At the same time, do you really think, Priyanshu, we have good engineers? Do you really think? Of course, I agree with your statement, but again, students who have completed their BTech or their MTech, you ask cross questions regarding the syllabus. They will say that we have done this long back, we have forgot. How much they remember? They only remember what they are working. Only that small portion they remember. So everything matters. Engineers are also not very good. Some engineers are there. Companies are also not sufficient. Of course, positions are less for us. See, why position is less for us? You understand one more thing. I will tell you. If you go to any street, I am talking about in general case, not any special case, you'll be getting so many shops for food, tea shops, hotel. But how many jewelry shops you see in any normal market? Only one. So we are those jewelry shops. We are very limited. That's why we are different than other engineers. Okay. We are high on our values, but we are not settled properly. It's okay. You can die. We all can die with this pleasure that we are aerospace engineers. Okay. Okay. Now we are going for. So I was saying that imagine this whiteboard is your aircraft. I mean atmosphere, and your aircraft is planned to go in this direction. So actually, someone will track the atmosphere. Someone will plan your route. So imagine we found that when your aircraft will pass this zone, here your atmosphere is not stable. So what do you mean by stability of atmosphere? So stability of atmosphere means, what is atmosphere? Atmosphere is nothing but at this location you'll be having gases, air, right? Air. So when aircraft will enter into this air should behave like technically what we are designed to, right? This aircraft. But what will happen? There is possibility this air molecule, like entire this thing, this may go up or down. There is possibility. This may go in this direction, in a direction. This may go, right? Point is why this guy will go. So right logic is, if this density, temperature, pressure is not exactly same as nearby atmosphere, then definitely this guy will shift or someone else will merge into this region. Okay, in that case, mixing of air, mixing of gases will start taking place here, or this atmosphere itself will shift to some other location. So when the shifting will happen, then there will be momentum in the molecules, right? So when aircraft will enter, then momentum will be transferred on the aircraft also, so vibration will take place. Okay. So we study stability of atmosphere. So what kind of atmosphere is suitable for us? What kind of atmosphere is not suitable? That is deep study. We are not going into that. Okay. So it means at certain conditions only our aircraft will go for a safe flight. Otherwise, they will cancel the flight or they will change the route. So you may have heard this thing. Just go little bit more physical. You may be aware of this drone concept. What happens in the drone? We have facility. We can, suppose this is a quadcopter, we can design the path of the drone, that this drone will go to point A, then point B, then point C. But in meanwhile, you can change to some other path also. Okay, go to A, but don't go to B, directly go to C. We have this facility. This path coding we do, and we dump into the chip, and that chip we put in this, and when chip is having that coding, then drone can see. Guys, how many of you are understanding this logic? Tick on the screen. Are you getting this path drone thing? Yeah, we can do this, right? So here maybe some gaming or something at very low level, but in aircraft also we have this facility. We can do that. I'm changing the page. So what my point is, there must be some basis on that we are going to define our atmosphere. So by comparing gamma and n, we judge stability of atmosphere. What is that? Copy down this. So if I will explain what is gamma, what is n. See here, we have a relation. Suppose this is your atmosphere. Here you have outside temperature is T1, P1, rho 1. This is the outside temperature. But exactly inside this gas, I mean this bulk amount of air, you have temperature T1 dash, P1 dash, and rho 1 dash. So because you see here, this guy is not matching with its surrounding, so definitely it will shift up or down. So I am considering this guy is shifting up. So now point is, this atmospheric values, when you will go into the attitude up, 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 suppose this is at from mean sea level, this is at H1 altitude, and when you will go up, suppose you are reaching here at this H2 altitude, so already you know that these values will change to T2, P2, rho 2, correct? But when this blue gas, when this blue region will go here and mix with these people, then again there will be a new value, right? T2 dash, P2 dash, rho 2 dash. So you can see here, this guy is not matching with its nearby atmosphere, so that's why it is shifting up. Now again, these people are not matching with their nearby people, so again they may further go up or they may come down. Okay, so it means what? In this zone you have motion in the atmosphere itself. So if any aircraft will pass through this, they will experience turbulence, right? So this particular situation is actually depending on the final element T2 dash, P2 dash, rho 2 dash, how they are behaving, correct? After mass transfer, you can see here mass transfer is happening, right? Mass transfer. After mass transfer, the new situation will judge. So that we can judge using this formula. I'm changing the page. You draw this diagram. Draw the diagram, then tick on the screen. I'm changing the page. So now I'm going to write down here equation rho 2 dash by rho 2, because there it matters finally where you are reaching. That we are going to compare with P1 by P2. See, 4 variables are different. Gamma minus n divided by gamma n. You will not get any numerical based on this, don't worry. Only thing is, this relation will help you to verify density variation. Okay, so just you draw the diagram, write down this equation, but you will not get numericals on this equation. You write down, if this gamma, you can see this n also, you can see here gamma, you know very well, adiabatic index, and n is any special value of the same index that we say as polytropic index. Okay, so if your gamma is greater than n, then only atmosphere will be stable. If your gamma is equal to n, then your atmosphere will be neutral. If gamma is equal to, is less is equal to n, then it is unstable. Stable means the mass transfer will return back. Neutral means mass transfer will merge there and it will not go further. Unstable means mass transfer will go ahead. Okay, this is the idea. But in GATE exam they will not ask these type of questions. But there is something called adiabatic lapse rate, another thing. So that adiabatic lapse rate we used to calculate using formula. This thing is important, this formula is not important. Now I am giving you adiabatic lapse rate. Changing the page. Take down adiabatic lapse rate. Here lambda A is the formula for that. So if lambda A is greater than lambda, then atmosphere is stable. If lambda A is equal to lambda, then atmosphere is neutral. If lambda A is less than lambda, then atmosphere is unstable. But what are these? What are these things? So idea is, there is a formula, n is equal to g by g minus lambda r. Okay, now this polytropic index n, this n is polytropic index. In thermodynamics we have done this. This is related to lambda. So idea is, if you will substitute this n value as gamma, this n value as gamma, that time this lambda will become lambda A. Then we will compare lambda and lambda A value. Okay, so that small note you can write down. Okay, I am changing the page. For n is equal to gamma, lambda becomes lambda A. Okay, so if you are substituting gamma is equal to 1.4 in the equation, because for air diatomic molecules are 1.4, so 1.4 is equal to 9.81 divided by 9.81 minus lambda A, adiabatic lapse rate, into 287. So your lambda A comes as 0.00976. So you can clearly see this is right now this data, when you are checking, this is adiabatic lapse rate. If you compare this value with all the atmospheric lambda, means lambda for troposphere, if you check, we have seen lambda today, that was lambda, it is, see, what is unit of lapse rate? Temperature by height, right? So Kelvin per meter, you can say. Just now we have done this now. Same lapse rate, it is also same lapse rate, but it is special in case of adiabatic condition. So this lambda A value, what we have got here, okay, unit also you write, otherwise you'll be confused. Kelvin per meter for this. Oh, you mean for this case? Okay, okay. So I was saying, if you will compare this lambda A value with lambda of different atmospheres, then you will say yes, which is stable, which is stable, which is not stable. So you see, for troposphere, if you check, then this lambda A is bigger than lambda for the troposphere, because in that case you have 6.5 only, here you have 9.7, correct? So this one is bigger. So bigger means it is stable. It means You can fly drones, aircrafts, helicopters in troposphere, no problem. If you will also check for stratosphere, there you have lambda 0. So again, your lambda A is greater than lambda. So that is also a stable condition. Okay. So that's why mostly we prefer these two layers of atmosphere. But again, there are other complications also we face in different atmospheres at different altitudes. So it's not like lambda is the only way to judge the flight route, right? So okay, fine. So we understood this concept of lambda and stability of atmosphere. So stability of atmosphere you can judge in two ways, one based on polytropic index and one based on adiabatic lapse rate. Two ways are there to judge the atmosphere. So once atmospheric like these formulas are done, you are ready to solve actually gate problems. Gate problems are really very easy. Now we are remaining with 6 types of attitude. So this thing I will take in next class. So I will stop class tonight. You all can leave. If you have any doubts, stay with me, ask your doubts. Thank you. Good night all of you.